so we need to review what we did last week. So we started talking about samples and populations. Who can tell me what a population is, what a sample is? Olivia was sick, so we got to make sure that she's on the same page as us. Right, what do you got?
Alright, so a population is like everything, like every item or person or something that is being studied.
So we're studying things, right?
Right.
We're trying to find out information. So the population is everybody, everything that is part of what we're studying. So a population could be as big as every single human on the earth. Or it could be as small as every 7th grader in the Accelerated 7 math class at Phoenix Middle School. Or even smaller than that.
That's 13.
A little bit more than that. No, 18.
18.
Because we've had people absent. Actually, well, 17 now because we lost.
A sample? Can I say that?
Yeah, what's a sample?
A sample is like a smaller group from the population.
So what do I use a sample for? I agree, it is a smaller group from the population. If you don't know, it's okay. I just figured I'd throw it to you.
I don't know.
For now?
To like test, like, so like if you studied them, then you could probably assume the rest of the people would be like that.
Ooh, what's that called? When I know something about the sample and I use that to make a statement about the population, that's called making an inference. So we can infer things based off what we know. So if you went to a sporting event and you see these people, you see 2 people very happy celebrating, and a larger amount of people kind of upset. It's the end of the sporting event, right? So the reporter knows nothing about the teams of the game, yet he concludes that the home team lost. Why would he make that inference? Why would he say that, Nate?
Assuming, well, it's a home team, so more people most likely should be at the game from that place.
Okay, so connect it now.
And then if they're sad, then that means the home team probably lost.
Yeah, the home team normally has more people at the sporting event than the away team. That's just kind of like the home team advantage. You don't have to go as far. So if the reporter sees more people that are upset, that you can obviously see they probably lost. If we see a big group of people that probably lost and a very small group of people that are celebrating a victory, we could assume, we could infer, you have to have data or something to base it off of. An assumption, you sometimes just assume without any data, without any knowledge. In inference, we have this knowledge. We know that more people normally come for the home team. We see that more people are sad. We can infer the home team lost. Yes, an inference is exactly like an educated guess. So we're going to use this information and this knowledge to be able to estimate the population. Now, what's really important about my sample? I need a blank type of sample to make sure that it's true or fair or going to actually match the population. Okay, so unbiased, yeah, but there's another word we use for it. Yeah, we need a representative sample to make sure that it's actually going to match. So on your paper, I need you to label the colors of your golf balls. The copy machine is obviously black, white, and it did not do a very good job of green and orange. So on your paper, label that the orange are the top 2. Orange.
Oh no. Oh, those red.
Orange are the top 2. And green are these. So now yeah, Zach. We maybe didn't get all the way through 15 but that's okay. I think you guys got the gist and you understood everything. We're pretty good at percentages at this point, I think most of us. One-third, right? So you see this worked out on your paper. We see that the number of orange golf balls, there's 2. Should probably capture this real quick. There's 2 golf balls out of the total 6. So when hello, come back to me. There we go. When I try to talk about part divided by whole, always make sure you're doing part divided by whole. I see most mistakes happen. Somebody would say, oh, well, 2 are orange and 4 are green, and they set up 2 over 4. Not right. 2 over 6. 2 orange out of 6 total. So that simplifies to 1/3. What percent is 1/3? Lily?
33.
33.
3300.
Yeah, 33.3 forever, right? But if you want to make your life easy, we would just use 0.33 or 33%, but that really does repeat forever. So we could say, since 1/3 of my sample is orange, 1/3 of my population will be orange, and then we estimate, well, there must be 50 orange golf balls, or very close to that, in the population. Do the same thing for the green balls. You probably only need about 30 seconds. Do the same thing for the green balls. Now, don't just say, well, if there's 150 total minus write out the work to match what we did here. So if 2/6 or 1/3 were orange, and then I multiply that by the total population to find my part that is orange, do the same thing for the green. Well, I was hoping to have smart ink because I like smart ink. There we go. Sheep?
That wouldn't be 2/3.
Yeah, well, what fraction did you use first? Unsimplify.
4/6.
Yeah, we see that 4 of the golf balls are orange out of the 6 total. That simplifies to 2/3. Then
Times it by 150.
you times it by the total population, and you got 100. So you end up estimating that there are probably 100 golf balls that are green in that population. Yeah. Question, Olivia? Yeah.
Sorry.
Are you going to say, couldn't you subtract?
Yeah.
Yes, but that's not using the method that we're talking about here. And the other situations will have more than 2 options. So you can't, most of the times you can't just subtract. But yeah, here we could have. So we're going to use this information and do that with robots. Like we talked, but we fall asleep for a very long time. A very, very long time.
What the? Oh no. I think I overslept.
Okay, really bad. I know. So it's 200 years in the future. Is this 200 important? No. Be careful when we get to those standardized tests. Watch out for the distractor numbers. Only pay attention to the numbers that matter to you. So the population is made up of humans and robots. If the total population of this town is 13,500 beings, not people, because robots aren't people, 13,500 members or beings, a robot can be a being, we want to estimate how many robots are in the population. How would I do this? What do I know based off what I see here? Olivia?
Are the green guy and the blue guy robots?
No, if you've ever seen the Jetsons, they always imagine that people in the future are going to wear like really weird things. But that's the futuristic clothing that they're trying to represent. I don't... Huh? So, look at the faces to determine robots. This dude has a face. The robots don't really have faces. Well, yeah, I know. They're kind of weird. So what do we know? Aside from that, people in the future apparently dress weird. Do you want to keep going or do you want me to move on?
We have 2 robots.
Yeah, we know that we have 2 robots. But 2 robots... What? I can't just use 2 robots, Ella? Out of 10 total. You always want that bottom to be your total. So really, we could say... We could simplify to 1/5, or we could say 20%. Either way. Then, what do I do? I've been loving all the hands. We can keep, yeah, right?
So, don't you have to multiply that times the 13,000?
What do you mean by that?
the 20% times.
Do you remember what we called it when we set up this fraction? It's
The
3
represent-
words.
Oh,
Blank of blank.
I don't remember.
Because this doesn't change. CP.
I don't know. Shoot.
So this value is the constant of proportionality. That's how my situation is proportional, because the population should be proportional to your sample. That's why we use the constant of proportionality. So like Rye just said, don't we need to multiply that? And then I stopped him. So I grab my constant of proportionality. What do we multiply it by?
The population. Right?
Yeah, I was really asking Rye, but I wasn't very specific. No, you're fine. I wasn't very specific with that. So what you might write somewhere in your notes is to get your estimate, we take the CP, or the constant of proportionality, times the population. That's all we got to do. So times my population of 13,500. This is when I like fractions. I would just use my 20% or my 0.2. Now, here's another easy method. 10%, I would just move my decimal over one place. So 10% would be 1,350. 20% is just going to double that. So we get 2,700, I believe. So there are 2,700 robots in the population.
That's a small city, or I don't know.
That's about the size of the town that I grew up in, actually. Well, the county. The county I grew up in, Coshocton, the whole county, and this was back when I lived there, there's probably less now, whole county had less than 12,000 people. Where if you look at Franklin County, it's like millions. Literally millions. There are more people in Franklin County than the entire state of Maine. Yeah. When my sister lived in Maine, we loved to reference that fact. We have more people in our county than you have in your state. And she would just always say, yeah, well, I have lots of room to do what I want. All right, so try the got it on your own while I fight with Smartink. Pay attention, this is a representative sample. That's why it works. It is a representative sample, 24 7th graders. There are 3 with April birthdays. I have an April birthday.
Happy birthday.
Suppose there are 448 students in the class. Last day of April. Which my sister thought was the 31st. I also will never let her live that down.
My dad's birthday was yesterday.
I don't know.
Nice.
My dad.
Happy birthday to you.
Oh, and my birthday.
Yeah, if you want to be a good kid, by the way, like kid to your parents. I don't like to call you guys kids, but you are your parents' kids. If you want to be a good kid, make sure you know your parents' birthdays. Save them in your phone, put them in your calendar, whatever, and wish your parents a happy birthday. It took me a while to realize that was polite to know your parents' birthday, considering that they made you. It's kind of the least that you can do. Anyone confident to walk me through this situation? I don't even care if you've solved it yet. I think that if you're confident, you can do this without solving it prior. Ooh, no, yeah, no, ooh, right.
Alright, so first off, there's 24 7th graders in this thing that we're doing. This
So 24 is the small
sample.
group. Yeah, that's my sample size.
Where's the sample? And then 3 of the students have the April birthdays.
Yeah, they have what I'm looking at.
The subjects.
Well, a subject is an individual. We would say they have what we're the characteristic we're talking about.
Alright, and then, so don't you have to, so for every 24 students, there's 3 students with an April birthday? Is
Yeah. How do I use that information to estimate how many have April birthdays out of the entire class?
That's your constant,
What is my constant
Your,
proportionality?
what's it called, 3/24ths?
Ooh, so I take the people that have my characteristic over the sample size, which that reduces to 1/8.
Yeah.
And then what do I do with that?
Multiply it by 448.
Yeah, so I take that 1/8, because to find my estimate, I take my constant of proportionality times the population, and we get, you know, 56. So we would estimate that we have 56 April birthdays. That's another piece of data that you could collect. I think I told you guys before the end of the year we're going to be collecting data on the either 7th grade or the entire Phoenix as a whole. So you could collect data on birthdays. It's kind of lame, but it is interesting. All data, even if it's a lame question, all data is interesting. Because we could find out that a lot of people have birthdays at the same time. This goes a little far in the conversation. What do you think causes birth rates to be more popular at one time of the year than other times of the year?
Sporting events.
Yeah,
Like
actually.
Super Bowl.
So he's absolutely right. Here's things that go into effect. Big events that were happening in the world. So like sporting events or whatever, because you know how you make babies. And weather. When people are trapped inside. We are moving on. But so when we collect this data, I want one of you guys to do birthdays. When we collect this data, it's interesting to look at where are more people, like where, because you're all around the same age, where are birthdays more likely and less likely? So how do we know there's a constant of proportionality? The word proportionality is the answer here. Because your sample has to be representative, for this to work, your sample has to be representative. That is going to be proportional to the population. So, because it is representative, it must be proportional to the population. Next year, you guys can have a deeper conversation with Mrs. Smith about that.
No. I'm having that right now, and every day when he comes home from school, constantly. No.
What is he like asking your parents questions or something?
No, he just talks about it like this and this happened, and this and this, and I leave the room.
Well, yeah. All right.
Clears the room.
Let me jump to your notes.
Is this the question that we have?
Yeah, but so this is showing you a data editor thing that we can use. So I'm just gonna jump to your notes real quick. This is gonna be tough. All right, check out the example on the back. Is a botanist. What's a botanist do?
Oh, it's like oh, I know, because I watched so much.
What's a botanist do? Olivia?
Someone, I saw this on a show when I was little, on the Little Einstein. So I don't know if I really remember correctly, but is a botanist someone that is like they kind of study flowers and plants and stuff like that?
Yeah, you study plants. So not just flowers, but like all plant life.
Yeah, right. You just
So a botanist wants to find the number of four-leaf clovers in a certain field. Now, four-leaf clovers are very hard. It would be very difficult to look at the entire field. So, there are 700 clovers in the field. What is that 700 then? Is that my population or my sample? Population, right? It's the whole thing. She has 3 samples from the population. If the actual number of four-leaf clovers in the field is 6, which sample best would represent that population? So, those are the things that you want to pay attention to as we go through this problem. Here's our 3 samples.
Clover as far as the eye can see. Patty sent me out to bring back a 4-leaf clover. A 4-leaf clover? I'll have to be incredibly lucky to find a 4-leaf clover. Nothing. I hope my luck changes soon.
So, we've got 3 samples. Don't go there. Stop. All right, maybe it has to go there, actually. Maybe I'll see if it needs to load. Okay, so my first sample. I find 1 4-leaf clover. Go away. It might be because I'm on the smartboard. Certain apps don't work with the smartboard because how it like clicks. So, This sample, how many four-leaf clovers did he find? How many four-leaf clovers in sample A? Well, so each box is a clover. The number's how many leaves it had. So, he found one, right? Out of how many? 5. So, we would do 1 out of 5. How many four-leaf clovers were in his sample? What percent? 20%. Do you think there's actually 20% of four-leaf clovers in the whole field? No. That sample, because the sample size is so small, it's a skewed sample. Lots of S words there, but a small sample will create your data skewed. So what we're trying to do is match what the actual situation is. So if I look at the actual situation, yeah, I was about to say move if you need. The actual situation, find the actual constant of proportionality. How do I find the actual constant of proportionality?
It's the
Zach?
You do like 6/700.
6 over 700.
the sample over the total amount of clovers.
Well, not the sample over the total. This 6 was not the sample. That's how many actual four-leaf clovers there are.
So that's equivalent to 3 over 350.
Yeah, and that can't reduce much further. So let's go ahead and do decimals for this guy. So what's 6 divided by 700 as a decimal, Jackson?
Wait, 0 and 8. Okay, I'm just gonna say it 'cause
Yeah.
I don't know how to pronounce it. Okay, 0.08571.
Wait, 0.0 or 0, 0?
0.0085714.
So that's far enough. Because now what we're going to do is use that. I'm going to capture it so it's up on the TV. We need to find what sample that the botanist took is closest to that. So sample A is right out. We know that's bad. Sample B, let's arrange that from high to low so that we can see how many four-leaf clovers are there easily. Well, sample B, they also only found 1. But then we have to say, well, how many total did they find? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, nope, 25. So they found 1 clover out of 25. What's 1 out of 25 as a percent? Do not touch your calculator. Or as a decimal, what do I do to make it easy?
Okay, you just multiply 25 by 4 and that's 100.
Yeah, I turn my bottom into 100. So I have 4 hundredths. Does that match 0.008? No. So notice sample C is bigger. It has still, I think, only 1 four-leaf clover. This is not working with me. So sample C would be your best sample there. All you do is you go through and you compare your constants of proportionality. So let's try the got it. We know that in this library there are 1,500 fiction books and there are 5,000 books total. So to find the actual constant of proportionality, what do? Yeah, 1,500 divided by 5,000. Shahid, what can I do with stacked zeros? Yeah, get rid of them. So this is really 15 over 50, which again, I can turn my denominator into 100 very easily if I double both of them. So I see that my constant of proportionality is a 0.3 30 hundredths or 3/10. And if I was approximating, we could say about a third of the library is fiction books. Gravity works. So now you got to figure out which sample is closest to your actual constant of proportionality. Take a minute and do this on your own. Which sample is closest to the actual constant of proportionality. So sample A, by the way, since they're just listing, like, this is a fiction book, a children's, a biography, another fiction book, a nonfiction, a poetry, and a play. Those are just listing individual books. Then down here, they're saying how many, like 12 fiction books, 15 non, 12 biographies. In sample A, how do I find that constant of proportionality?
Wouldn't you do 4 over 50 because they're doing 50? Oh, okay, I did the wrong one.
So we're trying to do constant of proportionality
I did the wrong one.
for fiction out of total. Okay, so erase it or fix it or whatever. Zach? How many fiction books were found in sample A?
2.
2, right? How many total books did I have in sample A? 7. And 2 sevenths comes out to be 0. What is it?
285.
Yeah, it's that whole 2, 8, 5, 7, 1, 4. There's a really weird one because sevenths actually have a pattern. There is a reason. You could go through and do the long division to see why the pattern happens. But remember, it chunks. The 28, the 57, the 14 always stay together. So it'll either be 0.142857 or 0.285714. Or the sevenths are really cool. So that's close. Not right there, but it's pretty darn close. We'll leave it for now. I'm just going to leave the whole thing written there. James, what about sample B? What math do I do there to find that constant of proportionality?
You do 12
Yep.
over 39.
Ooh, close. Ooh, wait. Yeah, 39's right. 12 over 39, when I do the division, what is it? 0. So it has some decimals after it, I bet. 30769. So now this one's actually closer than sample A. And then if I do sample C, Noah, what do I do there?
For number C?
Yep.
So what, you add them all together.
Okay. Take your bigger numbers first. 79, 99 plus another 9, 108 plus 7, 115 plus 19 more. I'm going to add 20 and then take 1 away. So
117. No. What was, I didn't know what your last one was.
79,
Yeah.
108, then 115. 134 is our total here, right? Can anyone verify that for me?
It's right.
So, what do I put on top?
The 40 fiction.
40. What do we get?
0.29850746.
So, we got to figure out which of these is closer. This is pretty darn close. It's like 1,000th away. This is 7,000ths away. So actually sample C is your best sample. Although they're all close, sample C is the closest. So we would use that one. Is this making sense? How we compare the constant and proportionalities. We just find which one's closest to the actual. So I'll probably just end up giving you guys time to work on your masteries tomorrow because we don't have a ton of time left. So we'll just finish this and then I got some papers to pass out. So if a computer factory has a total of 670 computers in storage and 3 inspectors each check 50 of the computers because they don't want to check all of them. They're just trying to get samples. So you see Inspector A, B, and C, how many defects they found. Which inspector's estimate, like which inspector had the best sample to match when we see, or sorry, I'm getting ahead of myself. We want to use their sample to predict how many defective are in the whole stock. Because I don't know how many are defective in the whole stock. B then tells me how many are defective, but don't act like B doesn't exist right now. We don't know how many are defective. So, how do I, Seth, find Inspector A's constant of proportionality?
You do 4 over 670.
Now, did that inspector check every computer?
No.
How many did each inspector check?
7. I mean, 50.
Each checked 50. So, for A, we would do 4 over 50, which comes out to be 800ths. Inspector B checks 1 out of 50, which comes out to be 200ths. And Inspector C finds 2 defective, which comes out to be 400ths. But I need to use those to estimate how many of the computers are defective out of the total supply of computers. How do we find those estimate values? No? No. So Inspector A essentially found that 8% of his computers were defective. B found that 2%, and C found that 4%. But that's of their sample. We want to estimate out of all of the computers. Ella? We take their constant of proportionality, because remember, to get an estimate, we do the CP, constant of proportionality, times the population. So take that 0.08, multiply it by 670. So 8% of 670 gives us, 53.6. So since we can't have a partial computer, we'll round that up to approximately 54. 5 looks kind of weird. 2%, well, I can do this easy. 1% would be 6.7 because I can move my decimal over to find 1%. So then double it. So I get 13.4 or approximately 13. And this is actually going to come out to be close to 27 when I round it. So then we're told, hey, there were actually 29 defective computers whose sample had been closest to accurate. Nate? Yeah, C was closest to accurate because it's the closest to the actual number of defects.
But they can't really help how accurate they are.
I know. So we're not like, I'm not going to fire anybody. I'm not making any judgments off this. We're just saying which sample had the, closest to accurate. Because then we might look at, well, how did you collect your sample? Like Inspector A, how did you collect it? Inspector B, because obviously whatever Inspector C did was very, very close to true. So, that kind of brings up the sampling method comparisons then. because not every sample is created equal, obviously, as we know. Try the got it while I pass some stuff out, and we will wrap that up and be done. So the got it is exactly like that. By the way, I'm going to pass back your what was the date? No, I'll hang on to these for now. I'll give you time to work on chapter 22 tomorrow. I was going to pass them back and tell you guys you could do it for homework, but that's not cool. Why? You want extra homework? Why? What, do you have like nothing else to work on?
Seriously, nothing else.
Okay, so then that brings up the question, if I allow you guys to have your masteries and leave class with them, can I trust you not to use the internet as a resource?
Yes.
I'm perfectly fine with you using your notes. I'm actually okay with you talking with each other about this as well, because you can help each other out. So I'll go ahead, by the convincing of you guys, and pass back your chapter 22 mastery. This is not homework. You do not have to get this done. I will give you time in class tomorrow, but some of you don't have lots of homework and you want to use your AO time effectively. So tomorrow I will give you class time to work on these, but if you get done, you can obviously use that class time for other things then. So I'm going to pass these back. Once you're totally done, I do not want these back until they're totally done, but once you are totally done with this mastery, then turn it back in. Because I was going to start grading these and I realized most of you were not finished, so I was like, well, crap.
Wait, did you grade this?
No, because you were the only person who turned it in right now, so just hang on to it.
Alright.
If I collect them again, I'll do it whole class.
Wait, did I finish this?
No. Were you just listening to me at all?
I will.
I mean, you may have finished it, I don't
did,
know.
I
But
did.
most of you were not finished, so I did not grade them, since most of you were not finished. I would encourage you, even if you're done, because we have had like the weekend and everything else, I would look it over before you turn it back in. You can even compare with a classmate. I know, like, wait, what? You can even compare with a classmate if you want and check each other's answers, because then you can have some good conversations. Like, wait, how'd you figure that out? Or why is your answer different?
Conversations.
So I know that's pretty rare from me to say